Okay, you can see my slide. I hope so. Okay, so we are in S13, but it is a 14th seminar I'm conducting. We start with S0 because mathematics numbers start with real numbers start with zero. When you call about integers, when we are using integers, you start with zero. So that is what I did. I started S0. Now we are in 13, and today's uh, topic is sets, paradoxes, and crises in mathematics. So that's why in the last uh, S12, I started with sets. So some of the elements of sets has been there. So now we'll continue with the study of sets. But we are so much familiar with sets that I don't have to tell mathematics about the sets. I'll talk about history. So I'll first of all start with one slide which was taken from the previous uh, seminar yesterday. That is Cantor's infinity. Cantor's first set theory article was published in 1874 and contains the first theorems of transfinite set theory, which studies infinite sets and their properties. Now the problem started with this. Cantor. According to Cantor, the set is a gathering together into a whole of definite, distinct objects of one perception or our thoughts, which are called elements of the set. So that's what Cantor did. And second mathematician who has done a lot of work on set theory is Russell. Russell called a set a class. When mathematicians deal with what they call a manifold, aggregate, means, ensemble, or some equivalent name is common, especially where the number of terms involved is finite. To regard the object in question, which is in fact a class, are defined by the enumeration of its terms and as consisting possibly by a single term, which is which is in that case is the class. So for Russell, set it defines as a class. It looks as a class. Now, very interesting is this set called empty set. Of course, we will know empty set uh, when there is nothing. What do you understand? What do you understand by empty set? Very interesting. What are the elements of an empty set? If there is a set, there should be some elements. What are the elements of this empty set? So I'll give one interesting example. An example of an empty set. Cows grazing at the moon. So this is an example of an empty set because there is no cow in the moon. So saying that cows, whatever numbers of cows grazing in the moon is zero, is nothing, is nothing. It don't have any sense. So this is an example of empty set. I don't know whether you have thought of such an example for the class or not. So my thought was cows grazing at the moon is an example of empty set. The empty set is defined by such a symbol. There is nothing there, or by this symbol, then by this symbol in our textbook. And the interesting, when we are talking of COVID, Omicron is another symbol used for empty set. I don't know whether you know about it or not. Now we are in the Omicron season, so Omicron is empty set. So you don't have to frighten with Omicron because it's an empty set. There is nothing. Don't be afraid of Omicron. Okay. Now, here I have put a cover page of a Russian book. Here the number of the book is 112. That is 112 book I have shipped from Moscow to Nepal. And this book I bought on 9th October 69. Okay. It's called, this is a story of sets. This is a story I read 53 years ago because it was in 69 from the book Stories About Sets. So the Raskaji Amro's means the stories of set, which I bought on 9th October 1969. So this is the book. Some of the quotes I am going here. The story which is written in this book, I am trying to now tell you about the story written in this book, which I bought 53 years back, half a century, more than it, half century. This book was published on the same year, 1969. So when it was published in 1969, immediately I got a copy of this book. In just at the time, it was very cheap. Books were very cheap. I had just completed second year of my 5 years study of mathematics in Moscow at that time. I started at 69. So the story goes like this. It is called Volatile Cosmos. This hotel was constructed in a certain galaxy. We are talking about infinite numbers. It has infinite number of single-bedded rooms. Very luxury type of hotel. The venue of inter-galaxy seminar on zoology was held in this hotel. So infinity number of scientists from all the galaxies were accommodated here. Mr. Press, that is a pressman, so I just wrote as pressman. Mr. Press from Earth was deputed as an observer. He traveled to this galaxy in a superluminal spaceship, because to go to this hotel, he had to go in this very fast traveling spaceship, superluminal spaceship. So he went to observe this inter-galaxy seminar on zoology. Mr. Press had a doubt that he may not get a room, since the hotel must have fully booked, because there were infinite number of hotel and infinite numbers of people and occupied the room. So he was afraid that he may not get a room. At the reception, he was surprised when he did not see any board. The hotel is fully booked. No more accommodation. Sorry for the invitation. There are no board like this. The hotel is fully booked. No more accommodation. Sorry for the invitation. There are no board like this. The manager allocated Mr. Press room number 1. Mr. Press was really surprised. Room number 1 must have been occupied by somebody, but he was surprised he was given room number 1. The manager has moved the earlier guests to the adjacent room. So guests from room number 1 was shifted to room number 2, and guests from 2 to 3, and so on. So since they are infinite numbers, you can go on shifting. This is how room number 1 was made free for Mr. Press. What an idea. A few days later, a team of 99 observers arrived from different parts of the galaxy. Now see, now it was almost full. Now again 99 observers arrived. The manager moved the guests by 99 roofs. So all the observers were accommodated in room number 1 to 99 now, because there was our Mr. Press from Earth, and there are more 99 one. So there were 100 observers. So the accommodation in room number 1 to 100 was for observers. So participants of inter-galaxy seminars on zoology were accommodated in rooms starting from room number 101 and onwards. And so everybody was accommodated. So Mr. Press was still in room number 1. You can see nothing has moved. While the inter-galaxy seminar on zoology was in full swing, infinite numbers of delegates from all the galaxies came to the same hotel for inter-galaxy conference on astronomy. Mr. Press thought that the manager will not be able to accommodate the new guests. Now manager relocated all the guests to odd numbers rooms and freed all the even number rooms. So the previous guests were all put in the odd numbers, and so all even numbers become free. In this way, manager accommodated all the infinity numbers of new guests to the free even numbers. What a brilliant idea! The manager must be a clever mathematician. Otherwise, he can't do such clever things. That is a story I read 53 years back. Anyway, now we go back to mathematics. The mathematician Bernard Russell, 1872-1910. Bernard Arthur William Russell was born on 18 May 1972 at Trelake, Wales, United Kingdom, from UK. His parents were Viscount Amberley and Catherine, daughter of second. This was the Catherine. The mother was second Baron Staley of Andley. So it's a British system. At the age of 3, he was left an orphan and was brought up by his grandmother. Both his parents brothers expired, and at the age of 3, so he was an orphan, brought up by his grandmother. Instead of being sent to school, he was taught by governess and tutors, and thus acquired a perfect knowledge of French and Germany. In 1890, of course, he was an English person, so he had additional knowledge of French and Germany. In 1890, he went into residence at Trinity College, Cambridge. So, at the age of 18, of course. So he was born in 1872. So in 1890, he went into residence as his boarder student at Trinity College, Cambridge. After being a very high wrangler and obtaining a first class with distinction in philosophy, he was elected a fellow of this college in 1895. After 5 years studying there, so he was elevated to this wrangler post position. He has a distinction in philosophy. So this Trinity College is very popular college in Cambridge, and fortunately for me, you can see I have visited this Trinity College, Cambridge, for taken 7 September 2009, 2005 with my wife. I went there to attend an international conference on ICMA conference actually, because in 2007 the ICMA conference was to be held in Kathmandu University by honor my chairmanship, and so 2 years earlier it's a biennial conference. So I had to attend this 12th one in London, UK. So then I also visited Cambridge and also visited Trinity College. So this Trinity College, it has a very nice church here. Now coming back to Bernard Russell, in 1900 he visited the Mathematical Congress at Paris, very important congress, 1900, because there's a lot of interesting events related with mathematical development in 1900. He was impressed with the ability of the Italian mathematician Piano and his pupils, and immediately studied Piano's works. In 1903, he wrote his first important book, The Principle of Mathematica. So this is Bernard Russell's Principle of Mathematics cover page of his book, and some of the inside cover of the book. So while his friend Dr. Alfred Whitehead proceeded to develop and extended the mathematics logic of Piano and Frege, in 1910 he was appointed lecturer at Trinity College. From time to time he abandoned philosophy for politics. So he was also very interested in politics. In 1918 he was sentenced to 6 months imprisonment for a pacifistic article he had written in the Tribunal. Tribunal is a journal. His Introduction to Mathematical Philosophy, 1921, was written in prison. So when he was in prison for 6 months, he wrote this book, Introduction to Mathematical Philosophy, in 1919. In 1920, Russell has paid a short visit to Russia to study the contribution of Bolshevism on the spot. But there is one small story about this Russell. So in London, there is a Hyde Park. There is a park called Hyde Park. It is known as Hyde Park. So it is so popular that anybody can go to this Hyde Park and stand up and give a free lecture. There is no restriction. So one time, Bernard Russell, because he is a big politician, so he also wanted to have a speech. So what he did is he took a small wooden box, okay, empty wooden box. So he put the small wooden box. He stood on the wooden box and started giving a political speech. In the meantime, this wooden box was a bit rotten, so one of the plank tore away, and his leg went inside the box, and so there was a small disaster. So the plank was cracked and gone. Then he again stood up and he says, "Listen and see the weight of my argument. Even this wooden plank couldn't stand this, my argument," he says like this. So that type of man was Bertrand Russell anyway. In autumn of the same year, 1920, he went to China to lecture on philosophy at the Peking University. In 1938, he went to the United States, and during the next years taught at many of the country's leading universities in the US. Russell was elected a Fellow of the Royal Society in 1908, and re-elected a Fellow of Trinity College in 1944, long time. He was awarded a Sylvester Medal of the Royal Society in 1934, and De Morgan Medal of the London Mathematical Society in the same year, and the Nobel Prize for Literature, not mathematics, for literature in 1950. Some of his major publications from 1897 on mathematics are Foundation of Geometry, 1897, Critical Exposition on the Philosophy of Leibniz, 1900, Principle of Mathematics, Volume 1, 1903, Principia Mathematica, 3 volumes. It's in 3 volumes, 1910 to 13, with his friend Whitehead. Introduction to Mathematical Philosophy, 1910. And so these are some of his major works. Bernard Russell is the father of set theory. But now we are going to talk a bit of set theory. He struggled throughout his life to resolving problems related to set. He is one of the most important logicians of the 20th century. Russell discovered a paradox which bears his name in May 1901 while working on the principle of Mathematica in 1993. So there is a paradox known as Russell's paradox, about which we'll talk later on. During the 1950s and 1960s, Russell became something of an aspiration to large number of idealistic youth as a result of his continued anti-war and anti-nuclear protest. In 1957, he was a prime organizer of first Pugwash conference about the proliferation of nuclear weapons. Bernard Russell was the founding president of the campaign for nuclear disarmament in 1958. He was once again imprisoned, this time in connection with the anti-nuclear protest in 1961. Upon appeal, his 2 months prison sentence was reduced to 1 week in the prison hospital. He remained a prominent public figure until his death 9 years later at the age of 97. Now, 97. Bernard Russell died on 2 February 1970 in Penur and then Marionette Wales in bit of south, north of. So there are some postal stamps related with Bernard Russell. This is Indian stamp. India. In mathematical logic, Russell's paradox, also known as Russell's antinomy, is a set of theoretic paradox discovered by Russell in 1901. Russell's paradox shows that every set that contains an unrestricted comprehension principle leads to contradiction. The paradox has already been discovered independently in 1899 by the German mathematician Ernst Zermelo. I think Zermelo was from 1871 to 1953. So now we'll talk a bit of Russell's paradox. Before that, now I have one more story, which every one of us knows, Achilles and the tortoise. The paradox of Achilles and the tortoise is one of the most famous paradoxes on motion. According to Zeno's argument, Achilles can never overtake a tortoise in a foot race if he gives him a head start, a bit start. So you can see the tortoise is here. Achilles, one of the first greatest wrestling person who can run very fast. So tortoise is here. He is always on the behind tortoise. He will never overtake this tortoise. That is what is meant by Achilles and the tortoise. Now, when we talk about set theory, the illustration of set theory is given by Venn diagram. So let's also look a bit history of John Venn, 1834-1823. He was born on 4 August 1834 in UK. He was an English mathematician, logician, and philosopher noted for introducing the Venn diagram. Was educated by tutors and in private schools entering Bourneville and Clios College at the University of Cambridge, where he graduated with a degree in mathematics and became a fellow in 1857. The diagram that bear his name were introduced by Venn as a means of depicting relation of inclusion and exclusion between classes, or what is we call now sets. They consist of 2 or 3 intersecting circles, each representing a class, and each level with an upper class letters, bigger letters, letters. Venn developed his diagramming methods by symbolic logic. Symbolic logic was introduced by him in 1881. A work that was primarily a sophisticated defense of the attempt by the English mathematician George Boole. So there is a Boolean algebra to represent logical relations in algebraic terms. Venn extended Boole's mathematical logic and is best known to mathematicians and logicians for this diagrammatic way of representing sets and their unions and intersections. He considered 3 dishes S, R, S, and T as typical subsets of a set U. The intersection of these dishes and their complements divide U into 8 non-overlapping regions, the union of which gives 256 different Boolean combinations of the original set is R, S, and T. John Wayne died in Cambridge on April 4, 1923. At Hall University is commemorated by the Wayne Building, built in 1829. I don't know what you can see here. Stained glass window in the dining hall of John Bailey and Close College, Cambridge University, commemorating John Wayne. And the Venn diagram, you can see the Venn diagram, three circles over here. Now, that was a bit of set. Now, coming to Nepal. World Master Year 2000 celebration in Nepal was held in Nepal Tourism Board. When I knew about this happening of World Master Year 2000 long back, I wised too much that Nepal also have to hold this in some way, we should celebrate in some way, but our dignitaries, chairman of Nepal Master Society, they didn't know about the weightage of this World Master Year. They were not very enthusiastic of having such a conference in Nepal. But as I have told, the first conference in January itself in World Master 2000, I went to Macau for participation. After many hue and cry, in the final, at the end of year 2000, a committee was constituted by the Minister of Education, and Pusuraj Adhikari became a member from Kathmandu University. He was a member from Kathmandu University to celebrate it. And the opening happened in the Nepal Tourism Board over here. So I was deliberating something we are talking about. But it was a king and queen's photo. We have to put it here. It's in the Tourism Board hall. And now I have to relate this because now I'm telling something about crisis in mathematics. Because the articles coming here, the materials coming here is based on the paper presented at the National Seminar held in Kathmandu, Nepal on February 8 to 9, 2001 to mark the World Master Year 2000. So in Nepal, it was celebrated in February only. There are several crisis periods in the history of mathematics, so I am quoting from this article. To avoid further confusion and satisfactorily answer paradoxical results, a new and more rigorous foundation for mathematics was necessary. Till the end of 19th century, mathematics developed in the light of the definition given by Aristotle some 2,350 years back. And Aristotle defined mathematics as a science of quantity. Aristotle's syllogistic logic followed by the axiomatic methods of Euclid's elements provided logical and methodological underpinning for mathematics, which were regarded as definite for over 2,000 years, and nobody could change anything there. Greek number theory, that is arithmetic, which deals only whole numbers, could not adequately deal with the incommensurable magnitudes found in geometry. So geometry was considered more fundamental than arithmetic, because even diagonal of a square, we can't measure it, because if you take a square of side 1 and 1, the diagonal will have the value √2, which is incommensurable magnitude. So geometry was considered more fundamental than arithmetic. And for that, Descartes, 1596, was inventing coordinate geometry advances and understanding of how geometry can be reduced to algebra. So algebra took on a more fundamental role. So mathematics developed using the concept of infinitesimal by Isaac Newton and Gottfried Wilhelm Leibniz, actually, and which became the basic of differential calculus. The major advances in logic after Aristotle appear on the work of George Boole, 1964, which subsequently became Boolean algebra. So very important for logic. This was followed by the contribution of Gottlob Frege, 1948-1952. Frege exposed deficiencies in Aristotle's logic and offered instead of formula language, his formal language. Mathematics continued to develop and get diversified till the introduction of set theory by George Cantor, which we have talked last time also. Cantor turned the very simple idea of a set into a rich theory, which was taken as a foundation of modern mathematics. First part of 20th century already reflects the growing trends towards rigor and axiomatization. Mathematicians were trying to work out the foundation of individual branches of and mathematics as a whole. This process started from the end of 19th century and is still in progress with many ups and downs. So the following 5 major crisis periods are presented here chronically. Period 1, non-Euclidean geometry. Period 2, contour set theory. Period 3, Frege's logic. Period 4, then Russell's paradox. And period 5 is known as Hilbert's formalism. These are the 5 periods in the crisis, five major crisis periods. So, all the 5 periods I will shortly read here. Period 1, the non-Euclidean geometry. Introduction of non-Euclidean geometry, hyperbolic geometry by Nikolai Ivanovich Lobachevsky. We have talked about that all here. Was followed by discovery of other forms of non-Euclidean geometry and gave rise to the formation of alternative geometry. The discovery of an alternative geometry precipitated a crisis, for it showed that Euclidean geometry, based on seemingly the most very enthusiastic all these axiomatic assumptions, did not correspond with reality as mathematics has discovered. Because when we talk of other alternative geometry, then the sum of interior angles of a triangle is not always equal to 180 degrees. In 1874, Cantor published an article, this is period second, Cantor second. In 1874, Cantor published an article in Crises journal, which marks the birth of set theory. Between 1879 to 1884, Cantor published a series of 6 papers in mathematics annually, designed to provide a basic introduction to set theory. The invention of a theory of infinite sets was the starting point of a series of controversies and paradoxes. Cantor's process thus. Let's take the series 1, 2, 3 and added infinite numbers after this and denoted it by the symbol omega. So we have 1, 2, 3 and ends somewhere at omega. Let's go on extending this number. Series thus. 1, 2, 3 omega, then omega plus 1, omega plus 2, then we'll have omega plus 1 omega, so we'll have twice omega. So 1, 2, 3 omega, up to twice omega. Now we can extend it further. So this is twice omega, then twice omega plus 1, so we go on omega, then we have twice omega, 4 omega, and so on. After that will be omega into omega, which will be omega squared. Then after that there will be omega 3, and going still further, we have, you see, it goes to omega to the power omega. Now it's being more interesting but very difficult to understand. What are these type of numbers? We still try to continue, and so omega to the power omega to the power infinity. Now this is what is meant by Cantor's set theory. At this junction, things get a little complicated because we have omega raised to omega an infinite number of times. This is called epsilon naught. Epsilon is the last letter of the Greek alphabet. So then we have, then this is epsilon. What is here is epsilon naught. Okay? As the smallest solution of the equation. So we have to denote it by epsilon. And so Cantor did not stop at this junction. He also created another set of infinite numbers, the cardinal numbers, which are harder to understand. Cantor's cardinal numbers measures the size of infinite set. Okay. Cantor's first infinite cardinal is Aleph naught. Aleph is the first letter of the Hebrew alphabet. Okay. So we have Aleph naught, which means the size of the set of natural numbers. Then comes Aleph 1, which measures the size of the set of all subsets of the natural numbers, which turns out to be the same as the size of the set of all real numbers. So natural number to real number. Then comes Aleph 2, which measures the size of the set of all subsets of the set of all subsets of the natural numbers. Continuing in this way, we have now Aleph 2, Aleph 4, and so this Aleph also goes on increasing. Thus, we take the union of the set of natural numbers with the set of all its subsets, with the set of all subsets of the sets of all its subsets, etc. And so it goes inside, it becomes more and more complicated. Then we get Aleph omega. Now you can see this very big cardinal number. Proceeding in this way, we get bigger and bigger cardinal numbers. We can even have very, very big cardinal numbers Now, LF epsilon. This is an outstanding feat of imagination. We see that the subscripts of Cantor's cardinal numbers are precisely all the Cantor's ordinal numbers. So we have infinity and larger infinity. So Cantor's work were very influential, leading to point set topology and other abstract field in the mathematics of 20th century, but it are also equally controversial. So that was Cantor's. Now, third period was Frege's logic. For 2000 years from the time of Aristotle, mathematician has been a science based on deductive logic. What an account of logic and had ever been produced which are adequate for the purpose of mathematics. Frege was able to devise a logic which could provide sufficient for the formalization of mathematics. Frege showed how this could be done in his book that Bruce Gaethje, this German word, their arithmetic, the logical foundation of arithmetic, which was published in 1893. He showed how arithmetic could be formalized in his new logic. So Frege's logic was soon shown to be inconsistent by Russell's paradox, but within a few years, alternative logics were devised which incorporated the essential advances made by Frege while avoiding inconsistency. So Russell, along with Alfred North Whitehead, his friend, in Principia Mathematica, devised the set theory of types and demonstrated how this could be used to formalize mathematics. So this is book of Principia Mathematica by Whitehead and Russell, volume 1. There are 3 volumes and inside cover. So inside started like this one. So published in 1963, reprinted in Cambridge at the University Cambridge, the University Press over here. Now the fourth period of Russell's paradox. Though Cantor discovered some paradoxes in his own theory, the ultimate paradox was found by Bernard Russell in 1902. It simply defines a set A is a set of X, where X is not a member of X. Now, very strangely, A is a set of X, where X is not a member of X. What does this mean? So it is so funny. Russell then asks, is A an element of A? Both assume so that A is a member of A and A is not a member of A, this way contradiction. So when you define a set in this way, A is a set of X elements where X is not a member of X. So this is known as Russell's paradox, which can be very nicely illustrated by the diagram which will come in the next slide. Russell's paradox arises as a result of Nave's set theory's so-called unrestricted comprehension axiom. The axiom states that any predicate expression Px, which contains X, has a free variable, will determine a set whose members are exactly those subjects which satisfy Px. This paradox is popularly known as the Barber paradox. So I have put a picture here. So this is Carton of Barber paradox. Now the paradox is like this. This is a barber, shave or not to shave. So there was in a garrison, group of army. Then there was an order that only those who don't know how to shave should go to the barber and shave. Those who know to shave himself should shave himself. He should not go to the barber. Now, well, okay, it was so simple rule. So those who, I don't know how to shave, so I went to the barber and shaved it, so finished. Now, who don't know, so they go to the barber and shave it, finished. So if I know, I don't go to barber, I shave myself. Now, when the barber had his long hair, braid, then he wanted to shave it, but he was so confused. So he knows how to shave it, so he should go to the barber. He should not shave himself. So now he is standing in front of a mirror and trying to see whether he should shave or not to shave. So this is known as barber's paradox. Now coming to the fourth one, Russell's paradox is still continued. It is also closely related with a much older paradox, the liar paradox, which is also called Epimenides paradox, and paradox is the statement is false. Most attempts at resolving Russell's paradox has therefore concentrated on various ways of restricting on or abandoning this axiom. Russell's own response came with the introduction of this theory of types. Now, lastly, period 5 of the crisis, Hilbert's formalism. David Hilbert, 1860 to 1943, was the founder of formalism and held the position that mathematics consists solely in the generation of combinations of symbols according to arbitrary rules and the application of logic. His first important work in 1899 was to produce a definite set of axioms for Euclidean geometry without any appeal to spatial reference or intuition. In 1905 and again from 1919, Hilbert attempts to lay a firm foundations for mathematics by proving consistency, that is, that finite states of reasoning in logic could not lead to contradiction. As the leading mathematician of his time, Hilbert considered in his personal duty to defend mathematics against all attackers and skeptics. In order to defend the foundation of mathematics, Hilbert proposed in 1904 his famous program. According to Hilbert, the most vulnerable point in the fortress of mathematics was infinite. So Hilbert badly assists that infinistic mathematics can be fully validated. This is to be accomplished by means of 3-step programs. What are the 3 steps? The first step is to isolate the unproblematic finitistic portion of mathematics, is to isolate it. The second step is to reconstitute infinistic mathematics as a big elaborate system. The last step is to give phonetically correct consistency proof for the big system. So, in 1927, Hilbert wrote, with this new way of providing a foundation for mathematics, which we may appropriately call a proof theory, I pursue a significant goal, for I should like to eliminate once and for all the questions regarding foundation of mathematics. In the form in which they are now posed by turning every mathematical proposition into a formula that can be concretely exhibited and strictly derived, thus reasoning mathematical definitions and inferences in such a way that they are unshakable and yet provide an adequate picture of the whole science. I believe that I can attain this goal completely with my proof theory. So that's what Hilbert wrote in 1927. So now, to avoid all this confusion, we have to rebuild the matrix. So rebuilding of matrix. To avoid further confusion and satisfactorily answer paradoxical results, a new and more rigorous foundation of matrix was necessary. The effort to rebuild the foundation of matrix led to the foundation of individual topics and also the foundation of whole of the mathematics. Some of the remarkable works in building the foundation of individual topics in mathematics are Foundation of Geometry by David Hilbert, 1903, Foundation of Algebraic Geometry by Andrew Will, 1956, Foundation of Algebraic Topology by Samuel Eliensberg, 1952. All the efforts in rebuilding the mathematics led to the formation of following 4 schools: Logistic School of Bertrand Russell and Alfred North Whitehead, Formalistic School of David Hilbert, Intuitionist School of Elise Brouwer, Set Theory School of Mathematics of Nicolas Bourbaki. Bourbaki is French. Now, one after another. Logistic method of Bertrand Russell and Alfred North Whitehead. The logistic school, whose central figures are Russell, Whitehead, had as its purpose to reduce mathematics to logic. So they are reducing mathematics to logic. Logistics seek to establish the meaning of mathematical notation by defining them in terms of concept of logic. They say that mathematics is logic. Logic consists of analytical truths. Analytical truths are those which are independent of subject matter. Now, second is Formalistic School of David Hilbert. The Formalist school was founded by David Hilbert. Formalist, formalistic seek to express mathematics strictly formal logical system and to study them as such without concern for their meaning. Their primary motivation was to justify the mathematics of infinite sets. The formalists hope to express mathematics of infinite sets in such a system and to establish the consistency of the system by finite methods, formalistic methods of David Hilbert. If they succeeded in this, they thought they would have justified a thorny question of just how such sets are. According to them, mathematics is a process of manipulating symbols which need not symbolize anything. So, quote Gödel's incompleteness theorem showed on the formalistic one-term and their programs was untenable. What Gödel discovered was that if we just try to deal with elementary mathematics with 0, 1, 2, 3 numbers only, and with addition and multiplication, that's elementary number theory, and just try to have a set of axioms for this, is called Peano's arithmetic. Even this can't be done. Any set of axioms that try to have the whole truth and nothing but the truth about addition, multiplication, and the digit numbers 1 to 3 will have to be incomplete. More precisely, it will either be inconsistent or it will be incomplete. So Gödel's original proof is very, very complicated. It starts with a liar paradox and constructed a statement. This statement is unprovable. Let us construct a statement in mathematics. If it's probable, then it's false. That is, we are proving the false result. And if it's unprovable and it said that is unprovable, then it's true and mathematics is incomplete. So either way, we are in trouble. This is Gödel. Then there's another Turing's halting problem. 5 years after Gödel, Alan Turing, 1912-1954, found a deeper reasons for incompleteness, a different source of incompleteness. Turing derived incompleteness from uncomputability because he is the father of the computer system. Turing. Turing's remarkable paper of 1936 marks the official beginning of the computer era. According to Turing, the computer is a very flexible machine. It's soft hardware. It's a machine that can be simulate any other machine if it provides with a description of the other machine. Turing's key idea is the motion of universal digital machine. So, halting problem. There is no algorithm, no mechanical procedure, no computer program that can determine in advance if another computer program will ever halt. The idea is that, therefore, running a program P in order to be sure that P will eventually stop, it would be nice to be able to give P to a halting program H. H decides whether P will halt or not. If H says that P halts, then we run P. Otherwise, we don't. So, all these controversies are there. Just assume that we have a subroutine S that can take any program P as input and that S returns will halt or never halts and always get it right. Here is how we get into trouble. With this halting problem, subroutine S, we put together a computer program P that's self-referential, that calculates itself. Once this program P has calculated itself P using the halting program, subroutine S, to decide if P halts. Then, just for the heck of it, P does the opposite of what S predicts. If S said P would halt, then P goes into that infinite loop. And if S said that P won't halt, then P immediately halts. And we have a contradiction which shows that the subordinate S cannot exist. Subroutine S cannot exist. So this is a halting problem. Then we have the Institutia, this school of Brouwer. These institutions whose leader Brouwer are best known for his conservatism regarding mathematical infinitude. They are opposed to application of the law of excluded middle to statements involving mathematical infinitudes, as in a proof that makes the following form. Either there is a number with property P or there is not. If not, a consequence would follow. It knows is known to be false. Therefore, there is a number with the property P. Such proofs do not tell us what a number is in question and why is that property, and what is that property. Constructive proofs, by contrast, do provide their information, and intuitionists require constructive proofs of mathematical theorem. According to them, mathematics consists of mental constructions which have no necessary relation to external reality. Indeed, it is any such things as external reality. Now, the theory of mathematics in Nicholas Bourbaki. Euclid's work dealt with number theory and geometry, essentially all the mathematics then known. Since the middle of the 20th century, a gradually changing group of mostly French mathematicians under the pseudonym Nicolas Bourbaki has tried to emulate Euclid in writing a new elements of mathematics based on their theory of structures. Unfortunately, they have just missed one of the new ideas from category theory. So now we have to have new ideas because all the things we were discussing, there are some paradoxes, there are some plus and minus. So new ideas. Recent development in the direction of the foundation of mathematics has evoked new ideas. Some of them are described here. I am reading the article I have given to during the World Mathematical Year in Nepal regarding Crises in mathematics. Most promising current research in rebuilding mathematics is development of category theory by Saunders MacLean, 1909, and Samuel Ellensburg, 1913-1919. Category theory throws light on many mathematical structures. It has certainly been proposed an alternative foundation for mathematics. Category theory is to discuss properties of totalities, such as the set of all groups. This means that category theory would like to be able to use an unrestricted principle of comprehension, where this is known to give rise to problems of consistency. Inconsistent mathematics is the study of mathematical theories that result when classical mathematical axioms are asserted within the framework of non-classical logic, which can tolerate the presence of a contradiction without turning every sentence into a theorem. So, Robert A. Mayer in 1976 seems to have been the first to think of an inconsistent arithmetic theory. Now, we are very like to have consistent mathematics. Now, he is talking about inconsistent theory, because arithmetic theory. These theories provide the basic for a revived Hilbert program. Hilbert's program was widely held to have seriously damaged by Gödel's incompleteness theorem, according to which the consistency of arithmetic was unprovable without arithmetic itself. But a consequence of Mayer's construction was that within his arithmetic, it was demonstrated by simple finitary means that whatever contradicts there might happen to be, they would not adversely affect any numerical calculation. Hence, Hilbert's goal of conclusively demonstrating that mathematics is trouble-free proves largely achievable. We think that mathematics is static, eternal, perfect, but in fact, the past century has been marked by a great deal of anguish and lingering, hot attack, and controversy regarding the foundation of mathematics, regarding its basic tenets, regarding the nature of mathematics, and what is a valid proof regarding what kind of mathematical objects exist and how mathematics should be done. There is a new field of mathematics called meta-mathematics. Now you can see it's growing up to meta-mathematics, in which you attempt to use mathematical methods to discuss what mathematics can and cannot achieve, and to determine what is the power and what are the limitations of mathematical reasoning. So in meta-mathematics, mathematicians examine mathematics itself through a mathematical microscope. Is mathematics looking at itself in a mirror, asking what it can do and what it can't do. So now we have another topic called randomness in mathematics. Real reason for incompleteness may be due to the fact that there is also randomness in pure matrix. A case in point is elementary number theory, where there are very difficult questions. Take a look at the prime numbers. Individual prime numbers behave in a unpredictable way if we are interested in their detailed structure. It is true that there are statistical patterns, some patterns are there. There is the prime number theory that predicts fairly accurately the overall average distribution of primes. But as far as the detailed information of individual primes numbers, that looks pretty random. In 1960, uh, G.J. Kathmandu and independently some other people came up with some new idea. This new idea is now called automatic information theory. Some reasons of areas of research now coming back. Some areas of research related with the foundation of mathematics that are being intensively worked out at present are there are several methods of coping coping with the incompleteness phenomena, and this constitutes a currently active area of research in foundation of mathematics. The idea of basing all of mathematics at one simple concept set has exerted a powerful attraction. The implications of this idea are not yet fully understood and are a topic of current research. The last 20 years have been a revival of Hilbert's program. Recent uh, foundation, foundational research has revealed that although Hilbert's original program is not physically reducible, there are other formal theories which are physically reducible in the precise sense envisioned by Hilbert. So that was the article I wrote about 21 years back. Now I am showing some of the books I have in my library. So one book is this book. Uh, Here is the book was published by Problems of Mathematical Schools, and the title is Mathematics and Natural Numbers, Natural Sciences. Mathematica is stricto anonymous, Mathematics and Natural Sciences. There is a collection of 16 articles published on 1969. I purchased this book on 12th January 1971. Okay, there's one more book I have. So this book was published by Academy of Science Philosophical Institute, and is called Methodological Analysis, Methods of Logical Analysis. It is a collection of 17 articles which was published on 1977. I purchased this book on 14 February 1979. So, uh, so I have studied such type of books. So that's why I could tell you about these historical events and moments. And so for this time, so it was more rhetoric, uh, reading my own article, which I published and uh, presented in the World Mathematical Year in Nepal in 2001. Okay, so we'll have our next seminar on March 4, after 1 week. So now from February we'll walk into March. So we'll have next seminar on Friday, March 14. The title on the is usually S14, and on the mathematics theory, the title will be Mathematics and Economics. So earlier I have an idea to uh, talk about applied mathematics. Then I thought that it is better to talk on concrete applied mathematics. So I changed the title to Mathematics and Economics. So next time we'll be talking of uh, mathematics and economics, how mathematics has helped economists uh, to develop economics theories over here. So that will be my seminar next time, mathematics and economics. So it was such a rhetoric type of presentation today. Okay. Okay. So now we can discuss, we can talk, whatever you like.
ओके थ्याङ्क यू सो मच सर मलाई चाहिँ एकदमै इन्साइटफुल लाग्यो लाइक अलिकति सेट्सको होइन अगाडिको कुरो पनि कनेक्ट गर्नुभयो सरले सेट्सको सेट थ्योरीको डेभलपमेन्ट भयो होइन सेटको त्यो त्यसको हिस्ट्री एन्ड देन त्यो पछाडिको अलिकति त्यो प्याराडक्सको बारेमा चाहिँ यो जेनोज प्याराडक्स पार्पर्स प्याराडक्सहरू चाहिँ थाहा थियो मलाई होइन सायद त्यो म्याथसँग रिलेटेड जस्तो यो रुजल्स प्याराडक्सहरू होइन
जस्तो प्याराडक्स
सो
त्यो धेरै थाहा हुनु
हो मलाई चाहिँ एकदमै राम्रो लाग्यो सर म्यामहरूको केही क्वेसन छ भने दीपक सरले
मैले सुनिरहेको छु यो आफै मात्रै बोले जस्तो भयो अब हाम्रो धेरै साथीहरू उहाँहरूलाई विज्ञान छ बोल्नु
यो पनि यो अहिले म्याथमेटिक्स अहिले पनि
नेत्र सर
भन सुदीप
नेत्र सर
हजुर सर हजुर
यो हामीले त्यो प्राइम नम्बरहरूको चाहिँ यो स्लाइडहरू पाउन सकिन्न सर अस्ति प्राइम नम्बर्सहरूको अलि बढी उ भएको थियो नि
सबैको स्लाइड पाउँछ मैले केही समयपछि नेत्र कहाँ चाहिँ पिडिएफ फाइल पठाएको हुन्छु त्यो पिडिएफ फाइल जसलाई चाहियो उसलाई सेयर गरिदिन्छ
हस् सर नेत्र सर यदि त्यो हजुरले पाउनुभयो भने हामीले पनि यसो सेयर गरिदिनु होला है
आजको एकछिनपछि
होइन सरले सेयर गरिरहनु भएको छ अब म एकैचोटि कम्पाइल गरेर म सबैलाई पठाउँछु
हस् सर हस्
जसलाई रिक्वेस्ट गरेर उसलाई नेटले पठाइदिए भइहाल्छ नि कुनै सेमिनारको भन्यो भने पठाइदिए भइहाल्छ त्यो कम्पाइल भइरहेको छ त्यहाँ
त्यही त हो सर
चाहिन्छ भने फेरि त्यो भिडियो पनि हेर्न सकिन्छ हाम्रो
सरको चाहिँ त्यही त त्यो बुक कलेक्सन र आर्टिकल कलेक्सन देख्दा चाहिँ भेरी इम्प्रेसिभ लाग्छ है त्यो चाहिँ साह्रै ठुलो कलेक्सन बनाउनु भएको छ त्यो 2002 मा त्यो गणित भारतीमा चाहिँ सरहरूले लेख्नु भएको थियो नि हाम्रो कन्हैया झासँग त्यो आर्टिकल त मैले मेरो डिजिटेसनमा साइटेसन पनि गरेको छु त्यो आर्टिकल पढेको छु मास्टर पिस नै हो तर त्यो भेट्नलाई मलाई निकै गाह्रो परेको थियो त्यतिखेर मैले सरसँगै मागे जस्तो लाग्छ रमाइलो लाग्यो इन्फिनिटीको धेरै कुराहरू नसुनेको कुराहरू सुन्न पाएँ आज चाहिँ हामी सधैँ नै नसुनेकै कुरा सुन्न पाएको छ तर आज अझै झन् धेरै नसुनेको नजानेको कुराहरू
त्यो कम्पारिजन गर्नलाई धेरै गाह्रो थियो त्यो बेलामा 2000 मा गर्नलाई मैले धेरै मेहनत गरेको अहिले त म कहाँ भएको मेट्रोल कुरको चाहिँ साइडमा राखेको मात्रै दिएको छु आई हेभ नट डन एनिथिङ न्यू त्यो बेलामा को आर्टिकललाई मैले कुरको चाहिँ स्लाइडमा राखेको
सरसँग एक्ज्याक्टली कति छन् बुक चाहिँ अहिले सरको पर्सनल लाइब्रेरी सरसँग कति छन् कलेक्सन
300 प्लस म्याथमेटिक्स बुक छ
वाउ
डिफ्रेन्ट टपिक्समा छ त्यहाँ फेरि जनरली देयर इज नो टेक्स्ट बुक मैले अस्ति एकचोटि भनेको जस्तो हामी सोभियत सङ्घ पढ्ने बेलामा वी डोन्ट ह्याभ टु बाई टेक्स्ट बुक त्यो सेमेस्टर सुरु हुने बेलामा त्यो सेमेस्टरलाई चाहिने एक चाङ चाहिँ किताब चाहिँ नि लाइब्रेरीले ठ्याक्क कम्पाइल गरेर राखेको छ अनि आफ्नो कार्ड दियो त्यो किताब ल्याउने अनि सेमेस्टर समेत फेरि फिटाउने त्यहाँ लाइब्रेरी हामी टेक्स्ट बुक चाहिँ किन्नै पर्दैन जनरली द बुक्स आई हेभ आर मोर आउटर बुक भनौँ न त्यससँग रिलेटेड बुक
कति राम्रो सिस्टम बनाएर
एनालाइसिसको किताब भने यहाँ 20 वटा 25 वटा होला मका बट दे आर मोस्टली नट टेक्स्ट बुक बट रिलेटेड विथ टेक्स्ट अफ एनालाइसिस भनौँ न अलिअलको अस्ति एकचोटि अलिअल देखाइ पनि सकेँ 5-6 वटा किताब देखाइ पनि सकेँ डिफ्रेन्ट टपिक्सको फेरि म चाहिँ त्यो इन्ट्रेस्ट लिएर किताबहरू किनेर राखेको हुन्छु हाम्रो कहाँ नेपालमा साँच्चै चाहिँ म्याथमेटिक्सको बुक कलेक्सन गरेको छ पुष्पराज अधिकारीले होला उहाँले
सरकोमा धेरै छ
होइन उहाँ आफ्नो पर्सनल कलेक्सन पनि छ उहाँ कुनै पनि बुक एक्जिबिसन हुन लागेपछि उहाँ दौडिहाल्नुहुन्छ एउटा किताब किन्नुहुन्छ अनि अर्को चाहिँ नि म कहाँ चाहिँ यो विभिन्न टाइममा चाहिँ नि अमेरिकन म्याथमेटिक्स सोसाइटी यिनीहरूको चाहिँ नि त्यो बुक लिस्ट आइरहेको ए सर एकचोटि चिन्न लगाओस् भनेर खुरखुर चिन्न लगाउनुहुन्छ अनि हाम्रो लाइब्रेरीमा चाहिँ नि मजाको बुक छ हाम्रो सन्तोष मान सर एकचोटि काठमाडौँ युनिभर्सिटीको लाइब्रेरीमा आएपछि ओहो तपाईँहरूको लाइब्रेरी त म्याथमेटिक्सको विषयमा त त्यो भनेर कतिभरि किताब छ उहाँ छक्क भएर कतिवटा किताब उहाँले ल्याएर पढ्नु पनि भयो हाम्रो काठमाडौँ युनिभर्सिटीमा अहिले स्ट्याग्नेन्ट छ त्यो बेलामा चाहिँ नि मेरो नातिनी हो यो दे आर ट्विन्स एकजना मात्रै आइरहेको
छ नातिनी नै रहेछ अघि ब्याकग्राउन्डमा नोइज गर्नु
नोइज एकछिन यहाँ आएर हल्ला गर्छ यो टाइममा
हजुर छोराको छोरी सर
मेरो ड्यानली एकजना मात्रै छोरा छ अरू छैन छोराको छोरी हो यिनीहरू चाहिँ नि त्यही छोराको छोरी ट्विन दे आर ट्विन्स अर्को चाहिँ नि कहाँ गयो यो चाहिँ नि 1 मिनट पछि जन्मेको हो 1 मिनट अगाडि जन्मेको चाहिँ नि यहाँ आएन खोइ त अहिले कहाँ गयो जस्तो अहिले आज सबभन्दा पहिले जोइन गर्ने सरिता हो होइन?
सरिताजीको धेरै कमेन्टहरू थियो, तपाईँ बोल्नुभयो भने रमाइलो हुन्थ्यो, इन्साइटफुल हुन्थ्यो।
सर म एक्चुअली म्याथमेटिक्स ब्याकग्राउन्डको होइन, तर सधैँ क्लासरुममा म्याथको इक्जाम्पलहरू दिँदाखेरि चाहिँ मलाई एकदमै बुझ्न गाह्रो हुन्थ्यो कि। सो सधैँ डराएर कति भाग्नु यो म्याथमेटिक्ससँग, म चाहिँ अब जसरी भयो नि एक दिन पनि म अब सेसन नछुटाइकन बस्छु भनेर बसेँ। अनि मेरो लागि एकदमै सरले एकदम ओरिजिनको कुराहरूदेखि लिएर कहाँबाट त्यो कन्सेप्ट राइज भयो, कसरी त्यो भयो भनेर मेरो लागि त एकदम इन्साइटफुल सेसन भइरहेछ सर, एकदम
त्यहाँ
हेल्पफुल
स्लाइडमा
भइरहेछ।
दुईटा कार्टुनहरू छ, एउटा चाहिँ त्यो एचिलिस र टर्टोसको है, अनि त्यो बार्बरको होइन, त्यो मेरो त्यो सेट थ्योरीको जुन किताब देखाएको छु नि होइन, 53 वर्ष अगाडि किनेको त्यो किताबको चाहिँ नि कपी गरेर राखेको हो मैले त्यो किताबबाट निकालेर राखेको। अब 53 इयर्स किताब अहिले पनि म अब सेट थ्योरी कहिले पढाएको छैन मैले होइन, त्यसै सेट थ्योरी भनेर पढाएको छैन। तर त्यो किताब स्टिल त्यहाँ यति इन्ट्रेस्टिङ छ, त्यो चाहिँ नि होटेल कस्मोसको पनि मैले त्यहीँबाट निकालेको र 2-3 फोटोग्राफ, त्यो फोटो होइन कि त्यो कार्टुनहरू त्यहीँबाट निकालेर मैले त्यसमा राखिदिएको। त्यसमा राम्रो राम्रो अरू कार्टुनहरू राम्रो राम्रो कार्टुनहरू राखेको छ। त्यो रसामा